Welcome to our first week online. I hope you're doing well and that your family's doing well. We watched the video that was in the modules, Bunnies, Dragons, and that gave you an idea about what we mean by sampling, where we take the same size sample over and over again and calculate a statistic for that sample, and that statistic, such as a mean, will have a normal distribution. Also, to do these problems, we're going to need your z-chart. Remember, you can print that off of homework, or you may have a copy already. Now, the first thing we need to do is define the central limit theorem. This states as a sample size gets large enough, the sampling distribution of the mean is approximately normally distributed. Okay, so we're not talking about individual values. We're saying we're taking samples, getting the mean, and making a graph of that data or doing some kind of chart. This is true regardless of the shape of the actual distribution of the individual values in the population. So even like the dragons, that's not a normal distribution, but if we take samples the same size over and over again and calculate a statistic, those statistics will have a normal distribution. And again, notice the ing there. Now, what size sample is large enough? That's a question we need to answer here. If it states that the population is a normal distribution, that we can assume that, yeah, we can use the z-chart. Well, let's say it's not stated. Well, if our sample size is at least 30, we can assume a normal distribution for the sampling distribution of the means. Or any other statistics we're finding. If n is less than 30, what we'll need to be told is we'll have to have some statement that the population is normally distributed. And the mean of all samples, if we take the mean of the means, I guess you'd say, they will approximate the mean of the population. That would be, for the sample means it would be a mu with an x bar. We can assume that these are equal. Now, we're going to have some formulas, and they're very, very similar to Chapter 6, with just a slight difference. So as sample size increases, obviously the effect of a single extreme value becomes smaller. The formula for standard error, this is our symbol here. It's our sigma. It has an x bar. Is equal to the standard deviation of the population divided by the square root of n. So as n gets bigger, this will decrease. What they call the standard error will decrease. So we'll be using this formula here in the sample problems. And our z-value formula is going to look slightly different for the sampling distribution. Your z-value, remember, is your x-value, but of course here we're looking at means of the sample minus the means of all the samples divided by that standard error. And we're going to write that like this. So remember, your z-value is simply the difference between the sample mean, the population mean, divided by the standard error. So this is where the difference comes in. Let's go ahead and look over on the next page and do a problem. And we're given the population mean, the population standard deviation, and our sample size is 25, but they've already assured us that it is normal, so we don't have to worry about that. And we're looking at the probability that x is less than 95, okay? And again, x bar, very important. That also gives you a clue that you'll be using these formulas because these have x bar in them and the ones from Chapter 6 did not. Well, we've got to get our z-value, and our z-value is 95 x bar minus the population mean divided by the population standard deviation over the sample size. And for that, I got negative 2.5. And remember, when it's a less than, we don't have to do anything exciting. We can read it right off the chart. So we're looking at negative 2.5. And there's negative 2.5.0062. And I do like to draw my curve every time I solve a problem. Let's see, the population mean is 100, and we were looking at it being less than 95, okay? So let's see, between 95 and 97.5. Remember when we did a between problem, we took the probability of the larger, if you refer back to Chapter 6, minus the probability of the smaller. We've already calculated that. Let's find the z-value for 97.5. Work all that out, and for that, I got z is negative 1.25, excuse me. So I've got the probability that z is less than negative 1.25 minus the probability that z is less than negative 2.5. And if I go to my z-chart, negative 1.25, so negative 1.2 go over 0.1056. Minus the probability here. We shouldn't be getting a negative number. That would make no sense. Okay, greater than 102.2. Okay, now remember greater than, and we're looking at something like this. We have mean is 100. We're looking for x bar to be greater than, well, our chart always gives us values to the left under the curve. And so what we have to do is the probability that x bar is greater than 102.2 is equal to 1 minus the probability the x bar is less than 102.2. We convert that to a z-value. So I took 102.2 minus 100 divided by 10 over the square root of 25. And if you want to pause the video and work that out, you should get 1.1. Let's look up 1.1 on our z-chart. 1.1.8643. And don't forget, we are subtracting from 1. And that'd be about 13.57%. Okay, now remember back in chapter 6, we're working, I guess you'd say, backwards here. We're given a probability. Let's write that as a decimal. We can rearrange our formula. And if we rearrange our formula, what it's going to look like is, if I take my z formula, which is x bar minus mu over sigma over the square root of n, and I do some rearranging, I get x bar is mu plus z times sigma over the square root of n. Okay, let's find this in the body of our chart. And let's go ahead and draw a picture so we'll know what side of the chart we want to look on. Okay, so 65%, it's above what value? Okay, so we're looking at something like this. So our z value is going to be negative, okay? We're going to have to subtract from 1. So it's always a good idea to draw it. And that'd be 0.3500. And let's go and find that on our z-chart. Again, we're looking on the negative, and we had to subtract from 1 because we're on the, quote, wrong side. Sorry, I keep hitting that. So 0.3500. Let's see. That's pretty close. 50, that's probably too far away. 3500. That's a little bit closer. Let's use negative 0.39. So there's a 65% chance that my sample mean is going to be, let's see, mu was 100 plus my z-score times sigma, which is 10, over the square root of n, which is 25. And make that a little easier to see. And so my sample mean is 99.22. So there's a 65% chance that when I pick a sample, the sample mean is going to be above this value. And finally, we have one, and this is similar to one that we did also in Chapter 6. So like I said, it's very important that you go back and review Chapter 6. We're looking at a probability distribution, and we're saying that middle 70% is between what two values? Okay, so the middle 70% here. So what we want to do is we want to find the z here, and that's going to be a negative z, and this is going to be a positive z. Well, this little area here, remember these are equal. So 1 minus 0.70 divided by 2, that'd be 0.3 divided by 2 is 0.15. So this is going to be the z at 0.15. Tack on a couple of zeros because we'll be looking in the body for that 4-digit decimal. And then this one here, the area below it is this plus this, so this would be at 0.8500. Okay. So we need to find these z values. So the negative z value at 0.1500 from our chart, let's go to the negative side, 0.1500, 0.1500, we got that. Let's see. Probably going to be, I'd say, closer to here, which would be negative 1.04. Let's go ahead and find that positive z value at 8500. And you can see these are the same distance from the center, so you won't be surprised at what we find here. So the positive side, 8500, let's see, the closest thing to 8500 is going to be positive 1.04. And this will always happen in these problems where you have a symmetric situation, where everything's symmetric around the mean. So to get the lower value of x, they want to know what two values around here. To get the lower value of x bar, it would be mu, which is going to be 4.7 ounces. And that's going to be the negative 1.04. And the standard deviation is 0.40. Again, we have a sample size of 25. But we have been assured that this is normally distributed. And you work that out, and you're going to get 4.6168 ounces. Will be the average volume of that sample, or the average for the lower value, and then 4.7 plus 1.04, and that would be 4.7832 ounces. And so the probability is 70% that if we calculate a sample mean, it's going to be somewhere between these two numbers here.